Have you ever worked with big geospatial datasets that are slow to load and huge in size? Today, I will show you a modern solution called GeoParquet. I am the AI geologist guy. Hello and welcome to my new tutorial. This video is for GIS users, data scientists, Python developers, and people that work with geospatial data. We'll cover what GeoParquet is, why it's useful, and compare it to the popular GeoJSON format in terms of speed, file size, and ease of use in analytics. Then, we will dive into a hands-on tutorial using a real dataset following a step-by-step coding demo in Jupyter Notebook. And we will see the key takeaways for your geospatial workflows. Let's get started. First, let's talk about Parquet. Apache Parquet is an open source column-oriented data storage format created through a collaboration between Twitter and Cloudera around 2013. It was designed as a modern alternative to traditional row-based files like CSV or JSON. Unlike row-based formats where each record fields are stored together, Parquet stores data column by column. This column architecture means all the values from a single column are stored contiguously, rather than intermixing columns for each row. This design leads to several benefits. It allows powerful compression, since similar values are stored together, and it lets you read only the columns you need for a query without loading entire rows. The result is faster analytics on large datasets and smaller file sizes. Parquet files are not human readable, but they are self describing. They contain metadata about the scheme and data statistics. This includes min-max values for each chunk of data, which query engines use to skip reading irrelevant parts. Another key feature is partitioning. In big data setups, you can split a large dataset into multiple Parquet files organized by a partition key, such as date or region. Partitioning the data in this way lets query engines skip the entire subset of data that aren't needed. For example, you might store each day records in a separate folder or file. A query for one day only reads that partitioning instead of scanning everything. Combined with Parquet internal column stats, this makes data handling very efficient in distributed systems like Apache Spark. GeoParquet is essentially Parquet for geospatial information. It's an emerging open standard, backed by the OGC Open Geospatial Consortium, that defines how to store vector geospatial data. It means points, lines, polygons in Parquet format. In other words, GeoParquet adds conventions for vector spatial data so you can get a single file that can hold attributes and geometry optimized for big data use. GeoParquet extends Parquet by introducing a few important things. First, it defines how to encode geometry data in Parquet file. Geometry columns are stored in a binary format within the Parquet structure rather than as text. Second, GeoParquet adds standardized metadata for spatial info. For example, it records the coordinate reference system (CRS) of the data, the geometry type, and the bounding box for faster petitions. This metadata ensures that any GeoParquet compatible software knows how to interpret the geometry. Essentially, GeoParquet fixes the lack of built-in geospatial support in plain Parquet by specifying a common approach. It's important to note that GeoParquet is designed only for vector data, points, lines, and polygons, and not for rest. raster data. Traditionally, spatial data has lived in formats like shapefields or GeoJSON, which don't integrate well with big data tools. This is where GeoParquet comes into play with big data analytic services. Big advantage of this approach is that any tools that already read Parquet can at least open a GeoParquet file. It will see a normal table with some binary columns. Even if that tool doesn't have these capabilities, it won't crash. It just might not understand the geometric columns meaning. But specialized tools that support GeoParquet will recognize those columns as spatial data. This is analogous to how a geotiff works. An image software can open a TIFF, but these softwares read the extra geotags to know the image map location. It's supported by DuckDB, Tidal, GeoPandas, PyGeoAPI, which can even serve a GeoParquet file as a web feature service via API, and because GeoParquet is just Parquet under the covers, cloud data warehouse and big data engines are on board too. Engines like Google BigQuery, Amazon Redshift, Databricks, and Snowflake can all work with GeoParquet and handle geospatial queries. Special softwares like QGIS and ArcGIS also can handle it. Beyond data warehouses, Apache Spark is another powerful option for working with GeoParquet at scale. While, while Spark can natively read a GeoParquet as it reads any Parquet file, it reads geometry as raw binary unless extended. This is where Apache Sedona comes into the game. It adds special data types, points, lines, polygons, functions like intersect, contains, or buffers, and indexing to Spark. Together, Spark and Sedona enable distributed geospatial analytics directly on GeoParquet datasets, stored in object storages like S3 in Amazon or Google Cloud or Azure, making it possible to run massive spatial joins and transformations efficiently across a cluster. It's useful because it also integrates naturally into modern ETL pipelines. Imagine an environmental agency processing daily updates of flood zone polygons. The raw shapefields are ingested into cloud storage, automatically converted into partitioned GeoParquet files enriched with attributes like population or land use, and then made queryable directly into a data warehouse or Spark environment. One of the limitations, however, is that GeoParquet cannot directly serve vector tiles for interactive web maps. For this case, you will need to use a service such as GeoServer, GoServer Tiles, or other tiling services that are in the market. Now, let's see a real scenario that involves GeoParquet in a modern workflow. Let's take a look to an imaginary case. In this case, an environmental agency wants to create an automated flood risk data management with Amazon Web Service serverless geostack. Previously, technicians uploaded shape fields manually, leaving analysts with weeks of cleaning and reprojecting work. Now, the company uploads to a S3 bucket these shape fields. This bucket triggers a lambda that has GeoPandas in it, which converts shapefield into clean GeoParquet and standardizes the CRS. On a weekly schedule, Event Bridge, a cron job, launches another lambda with DuckDB to join the geospatial data with population infrastructure stored as CSV. Calculating how many residents and facilities fall inside the reasons. The results are saved back to H3 as an enriched GeoParquet, serving as a single source of truth for dashboards, APIs, and planners. What once took weeks now happens within minutes, ensuring timely, accurate data for emergency planning situations. Now that we understand the basics of GeoParquet, it's time to move on from concepts to practice. In the following hands-on tutorial, we will explore how to work with GeoParquet step by step in a Python Jupyter notebook. Welcome to the exercise part. In the exercise, I have prepared two Jupyter notebooks, and we will do the same exercise in both Jupyters, but with the difference that one is with GeoPandas and the other will be with DuckDB. GeoPandas is a library very similar to Pandas, but with the main difference that is that it recognizes the geometry column as a real geometry. And you can do special queries and plot the data spatially. In the Jupyter, first we will download the data that we want to work, import GeoPandas, and load the Parquet. We can load it, check the number of rows, and plot it in a map. Then I convert the same file to GeoJSON and GeoPackage. GeoPackage is another type of file for storing vector data and raster data. Then in here I want to compare how much is the difference between the file sizes for the same information in these three different formats. So we can see GeoJSON, that's the only one that's human readable, is 23 megabytes, GeoParquet 15 megabytes, and GeoParquet, that's the most optimized, it's only 12 megabytes. For the loading time, in here we are loading as a geodata frame in GeoPandas these three type of files, and we can see the main difference is that GeoJSON takes a lot more to load it, and this is a small file. Usually when we are working in big data, we can work with files of 1 gigabyte or hundreds of gigabytes. And we can see the different times. And one thing to a point is that GeoParquet is 44 times faster than GeoJSON for loading the file and 1.5 times faster than GeoPackage. I want to say that one of the main difference between GeoPackage and GeoParquet is that GeoParquet it was developed to be a cloud native. It means that, for example, if you are working with a file that has 100 gigabytes, you can, and this file is stored, for example, in the cloud like an S3 bucket, you can load entirely in your PC or in a geodata frame a file of 100 gigabytes. And why it's useful, GeoParquet, it's because we can do a query to query only a bounding box or a set of rows that we want to work with them without loading the entire GeoParquet. In here we will do an example of a spatial analytics, and we will compare the time between working in GeoPandas and working with DuckDB. First we download both GeoPackage. We are working with the counties file, that's the same that before, and Microsoft buildings. You can see this URL that it contains a website where you can check this dataset. This dataset was created by Microsoft, and it has the buildings of all United States stored as a polygons. And it loads 1.5 gigabytes. So we can check the length. It's 129 millions of buildings or polygons. And because we want to do a special query, it's important to check always the CRS, because in GeoPandas you can do a special query between two different layers that are in different CRS. And for this way, we assigned to the counties the same CRS that has the Microsoft buildings, and check if both files or geodata frames in that case has the same CRS now that we have changed it. And then we select all the counties that are in Texas, and it gives us a result of 244 that is the real counties that has Texas. And then we do the spatial query as join, and this query, what it does is that select from the Microsoft buildings all the buildings, all the rows that are inside the other file, in this case, Texas counties. And now we have the dataset of we have the geodata frame of the Texas buildings. We put it to the CRS that we want, in that case 4326. That's latitude and longitude coordinates. And for this query, we have spent a total of 27 minutes. In this exercise, we have taken profit that we are using GeoParquet only loading the files, because then the information is stored as a geodata frame. But we'll work in the next exercise with DuckDB, and we will see that it's more faster and why it's more faster. Here we have the other Jupyter Notebook file. Both files will be in the description of my video, and I want to start it with a brief description of what it is DuckDB. DuckDB is a SQL database managed system designed for fast analytical queries. And unlike traditional databases, DuckDB runs directly inside your application, similar to what it is SQLite, and is optimized for analytics in large dataset. It supports columnar storage, and this is why it is interesting in GeoParquet, vectorized execution, and SQL queries on files like CSV or Parquet, without the necessity of having to import all the data. And it's often described as a SQLite for analytics. Okay, then in this exercise, first we import DuckDB, and we will check the time that it takes between DuckDB and GeoPandas, and create the connection and load the spatial capabilities. As you can see, the syntax is very similar as SQL. It is a bit different, but if you are used to working with SQL, it will be very easy for you to get used to DuckDB. First of all, we read the two Parquet files and load them as a table. We can print the rows of the table, and as you can see, if it's well detected, it will print the geometry and instantly without you asking for it. It will print the bounding box of the row that you have selected. Then we select the Texas counties as in the other file and put both files to the same CRS. And then we create the new table. This is the same function as the sJoin. In this case, in IndexedDB, it's called join. And we select all the buildings that are inside the geometry of the Texas counties. We can print the plan of all the tables with the syntax of count. And then we save it as a GeoParquet. As we can see, it took only 32 seconds. And in this case, we have used all the potential of GeoParquet. This is one of the main reasons that is interesting to work with libraries similar or with TagDB when working with huge files and doing big data analytics. That's all for today. I hope you liked my video and you can follow the tutorial. And thanks for all. I see you in my next video, and don't hesitate to write in the comments what do you want for the next tutorial. Maybe it will be code geotiffs or PostGIS or server tiles. I'm thinking about it. I am the guy, I tell this guy. See you next time.